2.4 Rates of Change in Tangent Lines, Part 2. Remember, your objectives for this lesson are to find the slope of a curve at a point and to write the equation of a tangent line and a normal line. Slope of a curve at a point. The slope of y equals f of x at the point P, A, f of A, is the number m, so the slope is m, equals the limit as h approaches 0 of f of a plus h minus f of a all over h. So this is your instantaneous rate of change. You remember this from part 1. And this is provided that the limit exists. So the tangent line to the curve at P is the line through point P with this slope. Example 1, let f of x equal 1 divided by x. Find the slope of the curve at x equals a. Okay, so let me move these parts down. And we're going to use the formula from the previous slide. So this is the limit as h approaches 0 of f of a plus h minus f of a divided by h. In this case, our function is 1 divided by x. So this is really the limit as h approaches 0 of 1 over a plus h minus 1 over a all over h. Now we're going to simplify. So I can rewrite this large fraction as the limit as h approaches 0 of 1 over h times, well, let me just write this part first. Okay, but really I want these to be over one denominator, so I'm going to multiply this top and bottom by a plus h, and this one top and bottom by a. Okay. So we end up with a minus a plus h all over a times a plus h. When you distribute this -1 here, you end up with a minus h on top. And these cancel. Okay. Okay. And I can cross cancel these h's here, so I'm really just left with a -1 on top. So when I go ahead now and plug in my h, 0 for h, I get a -1 on top over a times a plus 0, which is -1 over a squared. So this is the slope of the curve at x equals a. Okay, part B asks, where does the slope equal -1/4? So what we're going to do is take the slope, we already determined that was -1 over a squared, and we'll set it equal to -1/4. And I'm going to cross multiply to solve this. So I have -1 times 4 is -4 equals -1 times a squared is -a squared. These both have a negative, so I'm going to divide by -1. That will also get my a squared by itself, so these cancel. 4 equals a squared. When I take the square root, I'm left with just a. And on this side, I get a plus minus 2. So when a is at 2, this is, remember, our x value. Let's find out the point. So our function was f of x is 1 over x. So if we say f of 2, we're going to have 1 over 2. And f of -2 is -1/2. So at the points 2, 1/2 and -2, -1/2, our slope is -1/4. Okay. Part C, what happens to the tangent to the curve at the point a, 1 over a for different values of a? To help us answer this question, I'm just going to sketch a quick graph of what we're looking at. So this is one of your parent functions that you should have memorized. And I have a curve this way and another one. Okay, like this. So this is y equals 1 over x, or f of x equals 1 over x. And you can see, looking at this graph, that our slope m is always negative. You could also tell by looking at the slope that we found. Remember, m equals -1 over a squared. So it is a negative number. You can see it's always decreasing. As a approaches 0 from the right, so if we are coming this way from the right, you can see that this slope is getting steeper and steeper. It almost looks like you have a straight line going straight up. So the slope there is as steep as you can get. Your m is approaching -infinity. It is negative because your slope is negative, always. And then as a approaches 0 from the left, this way, again, you're getting very steep to the point where it's looking like a straight line. Your slope is approaching -infinity. Again, it is still negative because your slope is always negative. As you move away from 0, okay, so if I'm traveling the opposite direction, you can see that it's starting to level out. It's still negative, but it is starting to level out. And we have this tangent line here at x, not tangent, sorry, this asymptote at x equals 0. So your slope is approaching 0, but it's not equal to 0. So slope approaches 0 as a moves away from 0, but it is still a negative number. Okay. So this here you could also call the difference quotient of f at a. This formula you're seeing all over this presentation. It is a very important formula. You do need to know it. If you hear the words difference quotient, this is what we're talking about. Okay. And the normal line to a curve at a point is the line perpendicular to the tangent line at that point. So one of your objectives is to write equations of normal lines. Normal lines are perpendicular to tangent lines. Remember, the perpendicular means opposite reciprocal slope. So it has opposite reciprocal slope of the tangent line. Example 2. Write an equation for the normal to the curve f of x equals 4 minus x squared at x equals 1. So the first thing that we need to do here is find the slope of the tangent line. So let's go ahead and write this out. We have the limit as h approaches 0 of f of, well, we're at 1, so I'm going to say 1 plus h. So x plus h is 1 plus h minus f of 1 over h. And our function is 4 minus x squared, so 4 minus 1 plus h squared minus 4 minus 1 squared over h. Okie doke. Limit as h approaches 0 of 4 minus, this is going to be 1 plus 2h plus h squared. Okay. Minus, well, 4 minus 1 squared is 1. 4 minus 1 is 3. So I'm going to write a 3 here to save myself some writing. Over h. Okay. And you need to distribute this -1 to these guys in here. So the limit as h approaches 0 of 4 minus 1 minus 2h minus h squared minus 3. And if you look for your like terms, you'll see 3 numbers here, here, and here. And 4 minus 1 minus 3 all cancels out. Okay, how's that for simplifying? So we have the limit as h approaches 0 of -2 minus h squared over h. These all have an h in them, so I'm going to say the limit as h approaches 0 of -2 minus h. Okay, so I just canceled out those h's. Okay, and again, to calculate this limit, we're going to plug in a 0. So we get -2 minus 0 is -2. Okay, so this is the slope of the tangent line. But I know that I'm looking for a normal line. So for the normal, we have the opposite reciprocal slope. -2 is really -2 over 1. We're going to flip the fraction and flip the sign. So this is the slope of the normal line, and it is 1/2. We do know what point we're going through. It's at x equals 1. Let's figure out what y equals at that point. So f of 1 is 4 minus 1 squared, which is 4 minus 1, or 3. And we're going to use point slope form, y minus y1 equals mx minus x1 to write this equation. So I know y is y minus y1 was 3 equals 1/2 is our slope, x minus 1, okay? So this is one equation of the normal. I'm going to change it into y equals mx plus b form to make it a little easier to graph. So I'm going to say this is y minus 3 is 1/2 x minus 1/2. So I was just distributing this 1/2. Now add 3 to both sides, and we have y equals 1/2 x plus 2.5. So plus 2.5. This could also be written as 5/2. Same thing. This is our equation. The instantaneous speed at any time t is the instantaneous rate of change of position with respect to time at time t, or the limit as h approaches 0 of f of t plus h minus f of t over h. So basically, this is still the instantaneous rate of change formula. The only thing that's changed is now you have a t here instead of an x or an a. Okay, so instantaneous speed is really instantaneous rate of change. Okay, find the speed of the falling rock from example 1 in section 2.1 at t equals 1 second. So, in case you don't remember that problem, I don't blame you. The problem says the position function of the rock that's falling is f of t equals 16t squared. Okay, so with this, we can just say the limit as h approaches 0 of f of t plus h minus f of t over h. So the limit as h approaches 0 of 16, t is 1 plus h squared, minus 16 times 1 squared over h. Okay. So we have the limit of, this is 16 times 1 plus 2h plus h squared minus 1 squared is 1, so this is just a 16 and an h. Okay, so now I'm going to distribute 16. We have the limit as h approaches 0 of 16 plus 32h plus 16h squared minus 16 over h. These 16s cancel. Now we have an h common to these three terms. One h will cancel from each term. So we have the limit as h approaches 0 of 32 plus 16h. If I plug in a 0 in that h, then I find the limit is 32. This means that the speed of the falling rock at t equals 1 second is 32 feet per second. It's a pretty fast moving rock. I would stay out of its way. So that is the end of this section, the end of this chapter.